Hi, everybody. So let's figure out how capacitors, parallel plate capacitors specifically, how do they actually do that? How do they store energy? Like, how does that actually work? So before we do that, I want to remind you that if I have a plate like this, and that plate has a certain area A, and there are charges all over the thing like that, we would say that the charge density is the total number of charges spread out over the thing. Let's put a couple more, divided by the area. So if I needed to know the charge, I would have to multiply the charge density by the surface area so we can figure out the number of charges. Also, and I'm not going to redo this derivation, but the near field approximation, as long as the area is very large, the near field approximation for the E field near a single charged plate is going to be sigma divided by 2 epsilon naught. Okay? Now, if I have two plates, here's one, and then nearby I have another. Oops, that is not going to work. Let's just draw it head on. And this one has the pluses on it, and this one has the minuses on it. If the E field is out and in like that, out of the positive and into the negative. And if that's true, then we say that the E field is the left-hand plate plus the right-hand plate. They're lining up with one another. So that would be the same as sigma over 2 epsilon naught plus sigma over 2 epsilon naught. So the E field for a parallel, this is a parallel plate capacitor, the E field is the sum of the two, the charge density divided by epsilon naught, like that. And it's a constant. And we typically would draw it, I'm going to redraw our capacitor here. We would typically draw it with the lines going all the way across, out of the plus and into the minus, like that. So this E field is a constant. We also know that the potential difference between the left and the right is equal to negative E times D, where D is the separation between the plates, like that. So where does that come in to the capacitance? So we now have an expression for the potential difference, negative E times D, and we have an expression for the electric field, and we also know that the charge is equal to the charge density times the area. So notice both the total charge has a sigma in it, and the E field has a sigma in it. So we're going to use these three ideas, these three mathematical ideas together. The definition of capacitance is the total charge divided by the potential difference between the left and the right plates. And don't forget, it cannot be negative. So it's really the absolute value, like that. So the total charge we know is sigma times A. And the absolute value of the potential difference is E times D. Oops, I made a stray mark, y'all. The absolute value is E times D, so now we have C equals sigma A on top and E times D on the bottom. And we have that the electric field in between the plates is sigma over epsilon naught. So watch what happens now. So I have sigma over A divided by sigma over epsilon naught times D. The sigmas cancel. The epsilon naught looks like a tau. The epsilon naught ends up in the numerator. So we're left with the area times epsilon naught divided by D is the capacitance of a parallel plate capacitor. And this is almost always what we use in this class. And, most small circuits are using parallel plate capacitors. I would just draw your attention to the fact that only geometry matters. And that's going to be true for all capacitance problems. Even though it looks like you're dealing with the charge divided by the potential difference, and we are going to be concerned about the ratio of charge to voltage. So C equals Q over delta V. This is true, but in this case, that also equals the area times epsilon naught divided by the distance. So even though the ratio of charge to voltage matters, that ratio is always actually going to be dependent on the geometry of your particular capacitor. The farther apart they are, if D is some bigger value versus really, really close together, that definitely has an impact. And if you look at this, you're dividing by d. So the bigger the denominator is, the more you're splitting up the numerator. So you're dividing by a larger number. So that would make the overall capacitance go down. So whenever d is a bigger number, whenever you're spreading them out, you're actually lowering the overall capacitance. They're supposed to be parallel like that. So a smaller d would have this c would be, and what we're doing there is separating them on the left and pushing them together on the right. So the C on the left would actually be less than the C on the right. The closer they get together, so if you push them closer together, you're dividing by a smaller number. If you pull them farther apart, you're dividing by a larger number. So capacitance goes up as they get closer, which is almost a strange reaction. Okay, hopefully this will clear up some of the confusion, and we can use this to move into other types of capacitor scenarios. All right, thanks.